In this section, we're going to explore forces, and we're going to do that primarily by looking at Newton's 3 laws. Okay, Newton had law 1, law 2, law 3. Before we go into Newton's laws, we're going to have to understand exactly what a force is and all the different types of forces. The problem with that is that often to understand forces, you need to know a little bit about Newton's 3 laws. So I'm going to give you an idea of what the 3 laws are very, very quickly. The first law is the law of inertia, and that says that every object wants to stay where it is or doing what it's doing unless you put an extra force on it. The second law says that every force causes a mass to have an acceleration. This is a very important equation, and we're going to use it quite a lot. In other words, if there is a force, there's also an acceleration, and there's a link between bodies that are accelerating and bodies that are having an unbalanced force applied to them. If something is going at a constant velocity, or it is still or stationary, then there is no unbalanced force. And the last law says that for every action, there is an equal but opposite reaction force. And we'll describe these in a whole lot more detail later on, but you've just now got a quick little overview before we go into different forces. So, if a force has a direction, don't forget that we are either pushing in a force or we are pulling in a force, and therefore it is a vector. When we studied vectors, we started looking at forces already. So if I said to you a boy pushed with 5 newtons and his sister came and helped him push the car with 4 newtons, how much force was being applied to that car? You would have said 9 newtons to the right. We know, therefore, that force is being measured in a unit called newtons. Forces can make something go faster. So, for example, if you're pushing someone on a swing, you give them an extra push and the swing goes faster. You can make an object slow down. You pull against the swing and suddenly that swing will slow down. It causes something to change direction. So, if, for example, something is approaching you, if you're running in a rugby game and you bump into somebody, both of you would change direction. An object can be compressed. You can take a sponge and squash it, or you can stretch an object. You can take some press stick and pull it apart to stretch it, and you can prevent an object from moving by balancing out the other forces. So you can resist some sort of a motion. All of those are what a force is able to do. Forces generally alter the state of motion. So if I have 2 or more forces, then we add them and we get what's known as a resultant force. In vectors, you already know the resultant is the combined effect of everything else. So let's define it. The resultant of any number of vectors is that single vector that has the same effect as all the vectors acting together. So I can either increase the velocity. I can make something go faster by adding extra force to it. So for example, if I'm continually adding force to the back of a rocket, for example, then this rocket will keep going faster and faster. If I want, I can slow something down. So the original force was going towards the right, but then I apply the brakes and it acts against it, and I would then subtract those 2 forces and get a resultant that was much smaller. And I can reverse something's direction. So in other words, if I were to kick a soccer ball against the wall and the soccer ball bounces back, and I can actually turn it around. So you're always landing up with a result of a number of forces. For this example, we could consider this block A, B, C, D as it goes along. And when I have got 2 equal forces in opposite directions, the resultant force is no force on this block at all. Remember, by the way, that if this block were on a table, it would have a weight downwards and the table would push upwards on it. That would be an equal but opposite force. That keeps things in balance, thank goodness. That way our food stays on the table while we're eating it. If, on the other hand, we've got a big force to the left and a small force to the right, I will result with a small force to the left. If two big forces are being applied to the left, I will land up with a big force to the left. Here we've got three forces. These two seem to cancel each other out, one to the left, one to the right, and then there's still this one over here, which is the resultant. If I need to draw a diagram to express these things, there are two types of diagrams. The first one is called a force diagram. Force diagram is actually a picture of the object. In this case, it's a box, so it's not a very complicated picture, but if you're drawing a force diagram of a car, you draw a little car over there. If it's a force diagram of an apple falling, you would draw a little apple over there. A man on a parachute, you would draw a little parachute man over there. And then you show the forces acting on the object as arrows. The forces must get a name, but they can kind of go in any direction. So this is pushing onto the box, this one's pushing away from the box, that's onto the box, that's onto the box, and it doesn't really matter. Let's think about this box on a table, by the way. Firstly, if I'm pushing a box on a table, let's put the table in place. Whoop, there's the table. So I'm coming along and I'm pushing this block. Does everybody agree that I would also have some friction over here that would act against the block? The block itself has some weight, but thankfully the table is resisting and an equal but opposite force is being pushed back onto the block. We call that force, and we'll discuss it in a bit more detail later, the normal force. All right. This should be labeled applied force. And this one over here is frictional force. So you always label them and everything so that you've got a clear idea. For a free body diagram, and this is what you're normally going to have to do in an exam, the object of interest is just drawn as a dot. Sometimes we'll use a square. So in this one we've got a square, but you could also have used a dot, okay? And all the forces acting on it have to be pointing away from the dot or from the little rectangle. There's no detail to the picture. So if I had a man in a parachute, I would not be drawing a man in a parachute. If I had an apple, I would not be drawing an apple. Every force must be named. I'm not so happy with these names. Notice the frictional force is away from the object, still pointing towards the left, okay? And I would then call that frictional force. Give it its full name. And then applied force is pointing towards the right, but away from the object. Again, I label it with its full name. Gravitational force acting downwards. Full name. And finally, normal force acting upwards. Full name. So if we're going to look at some free body diagrams, let's look at these different examples. Firstly, if we've got a book standing still on a table, it is going to have two forces, weight or gravitational force and the normal force. Those are going to be balanced and therefore they need to be approximately the same length. You draw them with a ruler, by the way, difficult to do on the iPad. A brick on a slope. So let's draw a slope over here and we can put a dot for a free body diagram. We've got a downward force, that's weight. It always acts directly towards the center of the earth, okay? It's standing still over there, it's on the slope, so something must be holding it up, we'll call that friction. And something must be preventing it going straight into the surface, so I've got a normal. Notice that the normal acts at 90 degrees to the surface. Notice all my arrows are pointing outwards. We've got a man in free fall. Our man is a dot. And he obviously has some weight or gravitational force acting downwards. And then it depends. He'll have, if he's just started falling, a little bit of air friction acting against him. If he's been going for quite a long time, the air friction will reach the same length as the weight. The air friction will never get bigger than the weight. Remember, friction can only oppose a force. It can't actually create it doesn't get a person to lift up into the air. It only works against it. So that's the person if it was going at constant velocity. If he's reached terminal velocity, then that's what his air friction picture is going to look like. What about a bullet that's just been fired out of a gun? So here's my bullet. Again, it's just a dot. And obviously it's in free fall, so it must have weight. And does it have a force pushing it forwards? The answer is no. There is not some little man behind here going push, 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 push. As a bullet is fired from the gun, there is an initial thrust. There is a force. But once it's gone out the barrel of the gun and it's in free fall, there are no forces driving it forward. In fact, all the time it is slowing down and it is experiencing a resistant force of air friction. Those are the only two forces acting on that body. If I now have a car, notice it's a dot again. A car has got a weight acting down. There is a normal from the road. It's going at constant velocity, so it has got a driving force. A car does have a little engine going and pushing it forwards all the time, which is working against, and these must be the same length, the friction of the road. Notice all those forces in the horizontal plane are the same length, so they cancel out. Up and down, also the same length, cancel out. And that's the constant velocity. There are no unbalanced forces on this object.